Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. Dear students, in previous lecture we were discussing M sequences and we stopped, and we are now today we are starting from the properties of M sequences. M sequences have several properties that makes them attractive for spread spectrum application. There are a number of properties I will discuss. First, property number 1, it is when an M sequence has 2 raised to power n minus 1 ones and 2 raised to power n minus 1 minus 1 zeros. Property number 2, if we slide a window of length n along the output sequence of n shifts, where n is equal to 2 raised to power n minus 1, each n tuple except the all zeros sequence appears exactly once. Property 3, there is one run of ones of length n, one run of zeros of length n minus 1, one run of ones and one run of zeros of length n minus 2, two runs of ones and two runs of zeros of length n minus 3, and in general 2 raised to power n minus 3 runs of ones and 2 raised to power n minus 3 runs of zeros of length 1. For many communication applications, the 0-1 sequence is changed to plus minus 1 sequence by representing a binary 1 with 1 and a binary 0 with minus 1. We define the periodic autocorrelation of resulting sequence as R of tau equal to 1 over n summation k equal to 1 and ranges to n b of k times b of k minus tau. Then we have property 4, the periodic autocorrelation of plus minus M sequence is R of tau equals to 1 for tau is equal to 0, n, 2n and R of tau is equal to minus 1 by n otherwise. Now look at figure 7.15. It shows the general autocorrelation case for M sequences and the autocorrelation function for M sequences generated by a 4-bit LFSR. In essence, correlation is a concept of determining how much similarity one set of data has with another. Correlation is defined with a range of between minus 1 and 1 with the following meaning. 1 means the second sequence matches the first sequence exactly. 0 means there is no relation at all between the two sequences, and minus 1 means the two sequences are mirror images of each other. Other values indicates a partial degree of correlation. Now I am going to discuss autocorrelation. Autocorrelation is defined in equation 7.10. It is a correlation of a sequence with all phase shifts of itself. Pure random data should have a correlation value close to 0 for all autocorrelations with a phase shift other than 0. The M sequence has this property. It can be shown that autocorrelation function of an M sequence with its single sharp peak. It is a powerful aid to synchronization by the receiver. A related function also important in the spread spectrum context, that is cross correlation function. In this case, the comparison is made between two sequences from different sources rather than a shifted copy of a sequence with itself. The cross correlation between two sources A and B is defined as R AB of tau equals to 1 over n summation k ranges from 1 to n A of k B of k minus tau. In general, the cross correlation value produced by matching a sequence with a random sequence is low, which has two advantages. Number one, the cross correlation between an M sequence and noise is low, and this property is useful to the receiver in filtering out noise. The cross correlation between two different M sequences is low, and this property is useful for CDMA applications because it enables a receiver to discriminate among spread spectrum signals generated by different M sequences. Now let us discuss an important topic which is known as gold sequences. M sequences are easy to generate and are very useful for frequency hopping, spread spectrum and direct sequence spread spectrum systems, and not used for CDMA. However, for CDMA direct sequence spread spectrum, M sequences are not optimal. For CDMA, we need to construct a family of spreading sequences, one for each user, in which the codes have well-defined cross-correlation properties. In general, M sequences do not satisfy the criteria. One popular set of sequences that does is the gold sequence. Gold sequences are attractive because only simple circuitry is needed to generate a large number of unique codes. A gold sequence is constructed by XOR of two M sequences with the same clocking. As you can see in figure 7.16a, it shows an example. In this example, the two shift registers generate the two M sequences, and these are the bitwise XORed. In general, the length of the resulting sequences is not maximal. Further, the desired gold sequences can only be generated by preferred pairs of M sequences. These preferred pairs can be selected from tables of pairs or generated by an algorithm. I repeat, Dixon 94 lists set of preferred pairs and describe the algorithm. Here we summarize the mathematical conditions that leads to a gold sequence. Suppose we take an M sequence represented by a binary vector A of length n and generate a new sequence A by sampling every qth symbol of A. We use multiple copies of A until we have enough samples to produce a sequence of A bar of length n. The sequence A bar is said to be decimation of the sequence A and written as A bar equal to A of q. The sequence A bar does not necessarily have a period n and is therefore not necessarily an M sequence. It can be shown that A bar will be an M sequence with period n if and only if GCD of NQ equals to 1. Here GCD is greatest common divisor. In other words, N and Q have no common factor except 1. For gold sequences, we need to start with a preferred pair A and A bar, where A bar is equal to A of q, that are both M sequences and that meet the following conditions. 1. N mod 4 is not equal to 0. That is, all n except 0, 4, 8, 12. 2 is q is odd and q is equal to 2 raised to power k plus 1, or q equals to 2 raised to power 2k minus 2 raised to power k plus 1 for some k. Now, third property is GCD of nk equals to 1 for n is equal to n odd value, and GCD of nk is equal to 2 for n mod 4 is equal to 2. For shift register of length n, the cross correlation of the gold sequences produced by a preferred pair is bounded by mod of r is less than or equal to 2 raised to power n plus 1 by 2 plus 1 for n odd, and r is less than or equal to 2 raised to power n plus 2 by 2 plus 1 for n even. Starting with the preferred pair, a set of gold codes consists of sequences, that is, D represents a 1-bit shift of A bar relative to A. To generate the gold codes from shift registers, we start with all ones vector set in both registers as an initial condition. The resulting sequence are XORed to produce one gold sequence. This yields the first 3 sequences in the set. To generate the remaining sequences, This yields the first 3 sequences in the set. I repeat, the resulting sequences are XORed to produce one gold sequence. This yields the first 3 sequences in the set. To generate the remaining sequences, the second of the first 2 sequences is shifted by 1 bit and XOR operation performed again. This process continues through all possible shifts, with each additional 1 bit shift followed by an XOR producing a new sequence in the set. For a preferred pair of 5-bit shift registers, it can be shown that for any shift in the initial condition from 0 to 30, a new gold sequence is generated. That is, a 31-bit shift is the same as the 0 shift. The gold sequences are the 2 initial M sequences plus the generated sequence for a total of 33 sequences. This is illustrated in figure 7.16b. Focus on 7.16b. In general, the period of any code in a gold set generated by 2 n-bit shift registers is n equal to 2 raised to power n minus 1, which is the same as the period of M sequences. There is a total of n plus 2 codes in any family of gold codes. As an example of the effectiveness of gold codes, for n is equal to 13, n equal to 2 raised to power 13 minus 1, and it will be equal to 8191. There are 630 M sequences as shown in table 7.13, as shown in table 7.3, as shown in table 7.3, and there exist pairs of these sequences whose correlation values are at r is equal to 703, while gold sequence guarantee the selection of pairs such that r is less than equal to 2 raised to power n plus 1 over 2 plus 1, and it will be equal to 129. Now I am going to discuss Kasami sequences. Another important set of PN sequences are Kasami sequences, which are used in some third generation wireless scheme. Kasami sequences are defined by a procedure similar to that for gold codes. There are 2 sorts of sequences: small sets and large sets. For n even, we can generate a small set of Kasami sequences containing m equals to 2 raised to power n by 2 distinct sequences, each with period capital N equal to 2 raised to power n minus 1. A set is defined I repeat, a set is defined by starting with an m sequences A with period capital N and decimating the sequence by q is equal to 2 raised to power n plus 1. It can be shown that the resulting sequence A bar has a period 2 raised to power n by 2 minus 1. Now we replicate a single period of A bar q times to produce a sequence of length 2 raised to power n by 2 minus 1 times 2 raised to power n by 2 plus 1, and it will be equal to capital N. For example, for n equal to 10, the period of A is 2 raised to power 10 minus 1, and 2 raised to power 10 is equal to 1024 minus 1, it will give us 1023, and the period of A bar is 2 raised to power 5 minus 1, and it will result in 31. If we observe 1023 bits of a sequence A bar, we see 33 repetitions of 31 bit sequence. Finally, we generate a Kasami set by taking n bits of A and n bits of A bar and forming a new set of sequences by XORing the bits from A and the bits from A bar. I repeat, finally, we generate the Kasami set by taking capital N bits of A and capital N bits of A bar and forming a new set of sequences by XORing the bits from A and the bits from A bar, as well as 2 raised to power n by 2 minus 1 cyclic shifts of the bits from A bar. It can be shown that the maximum cross correlation value for the set is 2 raised to power n by 2 minus 1. This is smaller than for gold sequences and in fact is optimal. The large set of Kasami sequences also consist of certain sequences each with period capital N equal to 2 raised to power n minus 1 for n is even and contains both gold sequences and a small set of Kasami sequences as subsets. A set is defined by starting with an M sequence A with period n and decimating the sequence by q is equal to 2 raised to power n plus n by 2 plus 1 to form A bar, and decimating the sequence by q is equal to 2 raised to power n plus 2 by 2 plus 1 to form A double bar. A set is then formed by taking the XOR of A bar and A double bar with the different shifts of A bar and A double bar. It can be shown that the maximum cross correlation value of a large set is 2 raised to power n plus 2 by 2. Here we conclude Kasami sequences. Now I am going to discuss orthogonal codes. Unlike pseudo-random noise sequences, an orthogonal code is a set of sequences in which all pairwise cross correlations are 0. An orthogonal set of sequences is characterized by the following equality. Now I am going to discuss orthogonal codes. Unlike Pn sequences, an orthogonal code is a set of sequences in which all pairwise cross correlations are 0. An orthogonal set of sequences is characterized by the following equality. Summation k ranges from 0 to m minus 1 psi kt psi j kt is equal to 0, where I is not equal to j, where m is the length of each of the sequence in the set, and psi I and psi j are ith and jth member of the set, and tau is the bit duration. Both fixed and variable length orthogonal codes have been used in CDMA systems. For the CDMA application, each mobile user uses one of the sequences in the set as a spreading code, providing zero cross correlation among all users. Now we will look into Walsh codes. Walsh codes are most common orthogonal codes used in CDMA applications. A set of Walsh code of length n consists of n rows of n into n Walsh matrix. That is, there are n codes each of length n. The matrix is defined recursively as follows: W1 is equal to 0 and W2n is equal to matrix of Wn, Wn, Wn and Wn complement. In short, first row, first column all will be replicating Wn, and second row, first column is replicating Wn, but second row, second column is complement of Wn. In short, the third group, first three groups are replicating Wn, and fourth group is inverse of Wn, and this expands in the same manner, where n is the dimension of the matrix, and of course denote the logical note, where n is the dimension of the matrix and overscore denotes the logical note of the bits in the matrix. The Walsh matrix has the property that every row is orthogonal to every other row and to the logical note of every other row. As you can see in figure 7.17, it shows the Walsh matrices of dimensions 2, 4 and 8. Note that in each matrix, 3 of the 4 quadrants replicates the next smaller matrix, while the lower right quadrant, that is shaded one, is complement of the next smaller matrix. In each case, the first row consists entirely of zeros and each of the other rows contains n zeros and n ones. Recall that to compute the cross correlation, we replicate 1 with +1 and 0 with -1. Orthogonal spreading codes such as Walsh sequences can only be used if all of the users in the same CDMA channel are synchronized to the accuracy of a small fraction of one chip, because the cross correlation between different shifts of Walsh sequences is not 0 if tight synchronization is not provided, PN sequences are needed. Now look at the slide with title Variable Length Orthogonal Codes. Third generation mobile CDMA systems are designed to support users at a number of different data rates. Thus, effective support can be provided by using spreading codes at different rates while maintaining orthogonality. Suppose that minimum data rate to be supported is Rmin and that all other data rates are related by powers of 2. If a spreading sequence of length capital N is used for Rmin data rate such that each bit of data is spread by capital N equals to 2 raised to power n bits of the spreading sequence, it means transmit the sequence for data bit 0 and transmit the complement of the sequence for the data bit 1. Then transmitted data rate is n times Rmin. For a data rate of 2 Rmin, a spreading sequence of length n by 2 equals to 2 raised to power n minus 1 will be produced the same output rate of n times Rmin. In general, a code length of 2 raised to power n minus k is needed for a bit rate of 2 raised to power k times Rmin. A set of variable length orthogonal sequences is readily generated from Walsh matrices of different dimensions. For example, see DINA 98 for description. Multiple spreading. When sufficient bandwidth is available, multiple spreading technique can provide highly effective. I repeat, now I am going to discuss an important topic that is known as multiple spreading. When sufficient bandwidth is available, a multiple spreading technique can prove highly effective. A typical approach is to spread the data rate by an orthogonal code to provide mutual orthogonality among all users in the same cell and to further spread the result by a PN sequence to provide mutual randomness. It means low cross correlation between the users in different cells. In such a two-stage spreading, the orthogonal codes are referred to as channelization codes and the PN codes are referred to as scrambling codes. Now we show an example of this technique with IS 95 standard. Inshallah, this example will be shown in coming chapter. Till now, we have discussed different spreading codes in which we discussed customized sequences, gold sequences, orthogonal codes, Walsh codes, variable length orthogonal codes, and we also discussed multiple spreading. This is the end of today's lecture. Inshallah, in next lecture we will be discussing our next topic, that is coding and error control, in which we will discuss method of error detection that will contain parity check, cyclic redundancy check, and block error correction codes, in which we will discuss block code principle, Hamming code, cyclic code, and convolutional codes, automatic repeat request, in which we will discuss flow control and error control. Till then, take care of yourselves, keep studying, keep yourself safe. Allah Hafiz.